Hello and welcome to Neat Prepco. So, last time we learned chapter 1 class 11 living world of class 11 biology, then part 1 part 2 organism population class 12 biology. Today we'll be starting with class 12th physics semiconductors. Again it will be line by line NCRT reading plus explanation, and it is a theoretical chapter. So we'll try to cover as much as we can. If not, then I'll make another part 2 for it. So without further ado, let's get started. So please open this is the last chapter, chapter 14 uh, of your part 2 class 12 physics textbook NCRT, page number 467. I won't be sharing the PDF. I prefer that all of you take a pencil or highlighter and with your NCRT textbook underline together as we go ahead. Okay, so let's get started. Semiconductor electronics, materials, devices, and simple circuits. Introduction. Devices in which a controlled flow of electrons can be obtained are the basic building blocks of all electronic circuits. So devices in which we can control the flow of electrons, okay, they are the basic building blocks of all the electronic circuits. Before the discovery of transistor in 1948, such devices were mostly vacuum tubes, also called as valves, like the vacuum diode, which has two electrodes, anode, often called the plate, and cathode triode, which has three electrons, cathode, plate, and grid, tetrode and pentode, respectively, with 4 and 5 electrodes. So before transistor was discovered in 1948, most such devices, okay, which control the flow of electrons, they were mostly vacuum tubes, also which are called as valves, okay, like the vacuum diode, which has two electrodes, anode, which was often called as the plate, and the cathode. um, uh, in cathode there is triode, which had three electrodes, sorry, and then there were triodes, and then there were so in that we had the triode, which contained the cathode, the plate, that is anode, and the grid. Then we had tetrode and pentode, which had 4 and 5 electrodes respectively. In a vacuum tube, the electrons are supplied by a heated cathode, and the controlled flow of these electrons in vacuum obtained by varying the voltage between its different electrodes. Vacuum is required in the inter-electrode space, otherwise the moving electrons may lose their energy on collision with air molecules in their path. In these devices, the electrons can flow only from cathode to anode, that is, only in one direction. Therefore, such devices were generally referred to as valves. Like in heart, we have valves which only flow in one direction. So, yeah. Then these vacuum tube devices are bulky, they consume high power, they operate generally at high voltage, that is 100 volts, and have limited life and low reliability. The seed of the development of modern solid state semiconductor electronics goes back to 1930s, when it was realized that some solid state semiconductors and their junctions offer the possibility of controlling the number and the direction of flow of charge carriers through them. Simple excitations like light, heat, or small applied voltage can change the number of mobile charges in a semiconductor. Okay, so firstly, we had So firstly, earlier, before transistor was discovered in 1948, we had vacuum tubes which are known as valves. Why they were known as valves, if the question comes, this is because they only the electrons only flowed in one direction, that is from cathode to anode. Okay, now triode, now anode was often called as the plate. So triode had three electrodes: cathode, plate, and grid. Then tetrode and pentode both had four and five electrodes. Now the vacuum tube. Okay, so it was somewhat like this setup. Okay, so this was the cathode, and they used to heat the cathode so that the electrons over here, this used to be vacuum. Okay, and the electrons would go to anode, and a specific voltage was applied, of course. Okay, and in order to control the flow of electrons. Okay, so here it's written that the electrons are supplied by heated cathode, and controlled flow of these electron in vacuum is obtained by varying the voltage between its different electrodes. So they used to vary the voltage in order to control the flow of electrons, and this used to be the anode. And in these devices, that's why it was known as, vacuum was necessary. Why was vacuum necessary? Because in the inter-electrode space, otherwise the moving electrons may lose their energy on collision with the air molecules. If we had any kind of medium in between, um, then they would lose uh, then they would lose their energy. Okay, so when electrons are going from cathode to anode, if they if there are air molecules in between and they collide with those molecules, then they'll lose energy. All right, so we do not want that to happen, therefore vacuum was necessary in such valves or vacuum tubes. Now these vacuum tubes, of course, it is such a big setup, so they were bulky. Then these are very important points, because the question comes, differentiate between the current semiconductor devices and the previous ones. Then you need to write these points. They were really bulky. They used to consume very high power. You can see we had to put varying voltages in order to control the flow of electrons. Then they used to operate 100 volts, generally high voltage, high power, 100 volts. Then they had limited life and low reliability. Limited life as well as low reliability. The seed of the development of modern solid state semiconductor electronic goes back to 1930s, when it was realized that some solid state semiconductors and their junction offered the possibility of controlling the number and the direction of flow of charge carriers through them. Okay, so in modern solid state semiconductor 1930s, it was realized that some solid state semiconductors and their junction offered the possibility to control the direction and flow of charges. So basically, they could control the direction and flow of charges in 1930s, the modern semiconductors, which were slowly starting to discover and invent. Simple excitations like lights, heat, or small applied voltage can change the number of mobile charges in a semiconductor. Note that the note that the supply and flow of charge carriers in the semiconductor devices are within the solid itself. While in the earlier vacuum tubes or valves, the mobile electrons were obtained from a heated cathode, and they were made to flow in an evacuated space or vacuum. So, in the current modern semiconductors, the electrons which were through smallest change in voltage or light or any other thing, those flow of charge carriers in semiconductors, they occurred within the device. It used to occur within the solid itself. Okay, in modern semiconductors it was noticed, whereas in the vacuum tube, the cathode used to be heated, and then it was made to flow through evacuated vacuum chamber towards the anode. So no external heating was required in this, no large space was required in this, none of this was required. It was not bulky, it was not heavy. They were small in size, they used to consume low power, they used to operate at low voltages. 100 volts was not required, very low voltage, and it had long life and high reliability. So all those points which were there for the vacuum or vacuum tubes or valves, you need to write the all the opposite points for modern semiconductors. So if the question comes, what advantage does modern semiconductor have over valves or vacuum tubes, then all these points need to be written. Even the cathode ray tube CRT used in television and computer monitors, which work on the principle of vacuum tubes, are being replaced by liquid crystal display LCD monitors. So earlier we used to have cathode ray tubes. In cathode ray tube, this same mechanism was there. The cathode was heated, electrons flowed from cathode to anode, but instead of just the anode, here behind it there used to be a fluorescent screen, okay, mostly made up of neon, and the moment the electrons used to strike this, then uh, we used to get the image. So in television, computer, those all those monitors earlier, they used to have this cathode ray tubes only used to be there, okay. But nowadays, in television and computer monitors, but nowadays this principle of vacuum tubes got replaced by LCD, liquid crystal display, which supports solid state electronics, in which solid state modern semiconductors are used. Much before the full implications of semiconductor devices was formally understood, naturally occurring crystal called galena, which is actually lead sulfide with a metal point contact attached to it, was used as a detector of radio waves. So you need to underline this is really important. Before full implications of semiconductor devices, that is the modern semiconductor devices, were formally understood, we used to detect radio waves through a we used to detect radio waves through a naturally occurring crystal which was known as galena, which was nothing but lead sulfide. With a metal point, we used to detect the radio waves. In the following session, we'll introduce basic concept of semiconductor, discuss some semiconductor devices like junction diode, bipolar junction transistor, a few circuits. Okay. So 14.2, classification of metals, conductors and semiconductors on the basis of on the basis of conductivity, on the basis of the relative values of electrical conductivity or sigma, or resistivity rho, which is actually opposite of conductivity, that is 1 by sigma. The solids are broadly classified. So now we need to classify metals, conductors, and semiconductors, okay, on the basis of their conductivity. Conductivity, we need to write it by sigma. So it is actually conductivity is 1 by rho, and rho is 1 by sigma. So it is basically resistance and conductance. Both are inversely proportional, right? Both mean the opposite. So um, so first comes metals. Metals, they are they have high conductivity, so of course they have low resistivity. Similarly, semiconductors, they have resistivity or conductivity intermediate to metals and insulators, okay, which means they are neither highly conductive nor completely resistive also. Okay, they are semiconductors, they are somewhere in between. We'll see the values, you'll understand. Then comes insulators. Insulators, again the opposite of metals, it will have high resistivity and low conductivity, or you can say low conductivity. So we know that metals, they allow current to pass, so they have high conductivity, they have low resistivity. Insulators, they do not allow the current to pass through them, do not have free electrons to flow, and the flow of electrons is only current, right? So So they have high resistivity and they have very low conductivity. So for metals, the values are 10 raised to power minus 2 to 10 raised to power minus 8 for resistance, and 10 raised to power 2 to 10 raised to power 8 for conductance. Okay. Now for insulators, it will be 10 raised to power 11 to 10 raised to power 19 resistance, and 10 raised to power 5 to 10 raised to power 10 raised to power minus 11 to 10 raised to power minus 19 for resistivity. In semiconductors, it's in between 10 raised to power minus 5 to 10 raised to power 6, and 10 raised to power minus 6, 10 raised to power 5 to 10 raised to power minus 6. So here you can see that for metals, the conducting value is in positive 10 raised to power 2 to 10 raised to power 8, whereas the resistance value is negative 10 raised to power same minus 2 and minus 8. Similarly, for insulators, you will see the resistance range is higher and positive 10 raised to power 11 to 10 raised to power 19, whereas the conductance is 10 raised to power minus 11 and 10 raised to power minus 19. In semiconductors, it's in between minus 5 to 10 raised to power plus 6 is your resistance range, whereas 10 raised to power 5 to 10 raised to power minus 6 is the conductance range. It's basically the same. So therefore, they are called as semiconductors. Okay, so here you can clearly see that the conductance range is higher. Here you can see resistance range is higher. Here both are almost the same. Therefore, they are called as semiconductors. The values of rho and sigma given above are indicative of magnitude and could go well outside the ranges as well. Relative values of the resistivity are not the only criteria for distinguishing metals, insulators, and semiconductors. So even though we have been given a finite range of if the conductance and the resistance values are this to this or this to this, then it is metals and insulators or semiconductors. Still, these are not indicative of whether this is what distinguishes metals, semiconductors and insulators from each other. They are not the only criteria to distinguish. Okay, they are just relative values and it could go outside this range as well. Our interest in this chapter is in the study of semiconductors, which could be elemental semiconductors, compound semiconductors. So what are elemental semiconductors and what are compound semiconductors? First, let's come to elemental semiconductors. Elemental semiconductors, as you can see, elemental, so silicon, germanium. Then when I say compound semiconductors, again you can see the word compound. These are pretty self-explanatory actually. If you go through it yourself also once, you will understand. So these can be divided into three: inorganic, organic, and organic polymers. Okay, so in inorganic, we have cadmium sulfate, gallium arsenic, cadmium cerium, indium, phosphorus, etc. Okay, these are the inorganic compound semiconductors. Elemental semiconductors: silicon, germanium, easy enough to remember. Inorganic: cadmium sulfate, cadmium cerium, gallium arsenic, indium, phosphorus. Organic: anthracene and doped phthalocyanines. Anthracene, doped phthalocyanine. Cyanine. And organic polymers: polypyrrole, polyaniline, polythiophene, etc. Polypyrrole, I have no idea what spelling I'm writing. Polyaniline, okay, no, it's correct. And polythiophene. So you need to remember these by heart. Polythiophene, okay. So let's go through again. Elemental semiconductors: silicon, germanium. Compound semiconductors: cadmium sulfate, gallium arsenide, cadmium cerium, and indium phosphorus. For inorganic, organic anthracene doped with phthalocyanine, and organic polymers: polypyrrole, polyaniline, and polythiophene. Thiophene. Okay, again, elemental semiconductors: silicon, germanium. Compound semiconductors: inorganic would be cadmium sulfate, cadmium cerium, gallium arsenic, and indium phosphorus. Then organic will be anthracene and doped phthalocyanine. Organic polymers would be polypyrrole, polyaniline, and polythiophene. Okay, now let's go forward. Most of the currently available semiconductor devices are based on elemental semiconductors, silicon, germanium, or compound inorganic semiconductors. So either we study elemental semiconductors, most used, or inorganic compound semiconductors. However, after 1990, a few semiconductor devices using organic semiconductors and conducting polymers have been developed, signaling the birth of a futuristic technology of polymer electronics and molecular electronics. So, after 1990, even though these two are the most important, after 1990, few organic as well as few organic, okay, as well as organic polymers semiconductors were formed, which tells us that there's a futuristic technology of polymer electronics and molecular electronics is there. In this chapter we'll restrict ourselves to inorganic semiconductors, particularly elemental semiconductors, silicon and germanium. The general by Okay, so here we are only going to mostly study this and this. Okay, now let's come to the on the basis of energy bands. All right, so according to the Bohr atomic model, in an isolated atom, the energy of any of its electrons is decided by the orbit in which it revolves. Okay, so according to Bohr's atomic model, in an isolated atom, energy of any of its electron is of course decided by the orbit in which it revolves. Bohr said that the energy of the atom is actually the energy of the orbit in which it revolves. So, but when the atom come together to form a solid, they are close to each other. So the outer orbits of electrons from neighboring atoms would come very close or even overlap. So what they are saying is, even though we know that if this is the atom, okay, if this is the atom and these are the orbits and this is an electron going in its orbit, even though we know that they have defined energy for each and every orbit, and the electron also has a definitive yeah, but when a solid is formed, then in a solid there are so many atoms here, and every atom will have um its own orbit. So sometimes these orbits, they may come very close or they even overlap like this. So when they overlap, this would make the nature of electron motion in a solid very different from that in an isolated atom. In an isolated atom, we know that this electron would revolve only like this, and when it needs to absorb energy or it needs to release energy, then it will shift from one orbital to another. But when it's very close and it's overlapping, instead of going over here, it may go here, and from there it will start jump to this, and it will, because it will make the electron motion very different basically. So inside the crystal, each electron has a unique position, and no two electrons see exactly the same pattern of surrounding charges. Inside the crystal, each electron has a unique position, and no two electrons can see the exact same pattern of surrounding charges. Because of this, each electron will have a different energy level. So each electron will have a unique position, okay, and both cannot see the exact same pattern of surrounding charges because they both have a unique position. Of course, they are not coinciding or overlapping. Because of this, each electron will have different energy level. These different energy levels with continuous energy variation from what are called energy bands. So what are energy bands? each and every no two electron have the same pattern of surrounding charges. That's why all of them have a different energy level, and these energy levels have continuous variation, with continuous variation form energy bands. Okay, so the energy so the different energy levels each and every electron has, these continuously with continuous energy variation form the energy bands. The energy band, which includes the energy levels of the valence electron, is called as the valence band. The energy band above the valence band is called as the conduction band. So if these all are the electrons, okay, these all are the electrons, then the valence electrons, what are the valence electrons? We know that if I say 281, so this is the valence electron, right? So valence band contains the valence electrons, that is the electrons which are in the last orbital, okay, valence orbital. And then above the valence band is the conduction band, okay, above the valence band is the conduction band. Now um, the energy band above the valence band is called the conduction band. With no external energy, all the valence electrons will reside in the valence band. If we do not provide any external energy, then all these valence electrons which are in the last shell, okay, all these valence electrons, they will reside in the valence band only, and the conduction band will remain empty, okay, if we don't provide any external energy. But if the lowest level in the conduction band happens to be lower than the highest level of the valence band, the lowest level of the conduction band is lower, it is somewhere here, than the highest level of the conduction band. So this is the conduction band, this is the valence band. Okay, this is valence band, this is conduction band. Here are all the valence electrons. So if we don't provide any external energy, then these valence electrons, they cannot be excited and they cannot go to the conduction band, okay, until and unless we give it energy. But if this is the conduction band again, and this is the valence band, so if the conduction band, okay, is lower than the highest level of the valence band, then then the electrons from valence band can easily move to the conduction band. So this is the highest level of the valence band, and this is the lowest level of the conduction band. So basically they are overlapping, so therefore all the valence electrons can easily move to the conduction band without any problem. Now normally the conduction band is empty, as I said, without, you are not giving, all are neutral, okay, you are not giving any extra external energy. If when you are not supplying any external energy, all the valence electrons are going to be in the valence band, they are not going to be in the conduction band. So usually the conduction band is empty, but when it overlaps on the valence band, then the electrons can move freely onto it. When the highest level of the when the lowest level of the conduction band is lesser than the highest level of the valence band and it overlaps, then easily the electrons can move to it. And this is what happens in metallic conductors or metals. We will read this in much detail ahead. So this is basically what happens in metals. Now if there is some gap between the conduction band and the valence band, then electrons in valence band all remain bound and no free electrons are available in the conduction band. This makes the material an insulator. So if both of them overlap, okay, or they get or they have very little gap, so that they have minimal energy, and basically all the valence electrons are freely able to move to the conduction band from the valence band, then we call them metals. But if there is a very significant amount of energy between the valence band and the conduction band, then no electron can move from valence band to conduction band, therefore we call them insulators. No external energy supplied, even if it's supplied, still the distance is so big between the valence band and conduction band that the electrons cannot move to the conduction band, then it is definitely an insulator. Now, but some of the electrons from the valence band may gain external energy to cross the gap between the conduction band and the valence band. Then these electrons will move into the conduction band. At the same time, they will create vacant energy levels in the valence band where the other valence electrons can move. Thus, the process creates a possibility of conduction due to electrons in conduction band as well as due to vacancies in the valence band. So, naturally, if we have electrons in the valence band, okay, and there is a good amount of energy gap, but the energy gap can be overcome if we supply external energy. So we supplied external energy and the electrons, they move from the valence band to the conduction band. Then the conduction band now is not empty. It has it is not empty, but the place where the electron was in the valence band, that place has become vacant. So then it is saying that these electrons will move into the conduction band, then at the same time they will create vacant energy levels in the valence band, because they are moving from valence band to conduction band. So that the other valence electrons can move. So from other lower energy bands, if this electron went to the conduction band, here an empty space is formed. Okay, you can also write the empty space with a plus sign, because it is an electron, it moved. So then now the other electrons will come and take the place of this electron. Okay, that move, this vacant energy level. And this process creates possibility of conduction due to electrons in conduction band, as well as due to vacancies in the valence band. So now electrons are moving to the valence band because there are vacant energy levels. So this has created the possibility of conduction, because the electrons have moved to the conduction band, as well as because more and more electrons have moved to the vacant places in the valence band. Let us consider what happens in the case of silicon or germanium crystal containing n atoms. For silicon, the outermost orbit is the third orbit, that is n is equal to 3, while for germanium it is n is equal to 4. The number of electrons in the outermost orbit is, you can find out the configuration of germanium and silicon. Okay. Um, the number of electrons in the outermost orbit for uh, 4, that is 2s 2p electron, hence the total number of outer electrons in the crystal is 4n. Maximum possible number of electrons in the outer orbit is 8, 2s 6p. So for 4n valence electron there are 8n energy level. These 8n discrete energy levels can either form a continuous band, or they may be grouped in different bands depending upon the distance between atoms in the crystal. At the distance between the atoms in the crystal lattice of silicon and germanium, the energy bands of these 8 and states is split apart into two, which are separated by an energy gap Eg. Okay, so they have taken an example of silicon and germanium, and we know that the in outermost eight electrons should be there. Okay, so 8n discrete levels should be there. Okay, in the valence band, but out of these only 4 are occupied. So 4n are so 4n valence electrons are there. Okay, we have 4n valence electrons are there. Now these 8n discrete levels can either form a continuous band or different bands depending on the distance we have between atoms in the crystal. Okay, now for the time being we are saying that, okay, 8n all come in the valence band, and out of that 4 in the valence band we have 4n valence electrons. So uh, the energy band of these 8n states is split apart into two, which are separated by energy gap E. The lower band, which is completely occupied by 4n valence electron at temperature of absolute zero, is the valence band. Okay, so if this is the conduction band, okay, Cn I'm writing, and then or you actually write it as Ec, and this is valence band Ev. Then the distance between the conduction band and the valence band is known as energy gap. Then they have told that this EV is completely occupied by 4n valence electron at temperature of absolute zero. Temperature is absolute zero. Okay, and 4 valence electrons, okay, 4n valence electron are completely occupied. The other band consisting of 4n energy states called the conduction band is completely empty. Okay, this has 4 n energy states. Okay, this is vacant. Basically 8n discrete energy level should be there, so they have split it into 4 and 4. Okay, so here also at temperature absolute zero this is completely empty. Okay, now let's go ahead. Let's go to the page 471, band theory of solids. You can just put a read, it's not coming. So the lowest energy level in the conduction band is shown as Ec, and the highest energy level in the valence band is shown as Ev. Okay, so this is the highest energy level of the valence band. This is called as EV. This is the highest lowest energy level of the conduction band. This is called as EC. So above EC and below EV, there are a large number of closely spaced energy levels as shown in 14.1. The energy band position in semiconductor at 0 Kelvin, the upper band called the conduction band consists of infinitely large number of closed spaces energy state. The lower band consists of closely spaced completely filled energy states. Okay, so above you can see that it contains the conduction band has infinitely large number of closely spaced energy states. Okay, whereas the lower one has closely spaced completely filled energy states. Now the gap between top of the valence band and bottom of the conduction band is called as the energy band gap or the energy gap. Okay, this is EG. We just learnt about it. Now it may be large, small, or zero depending upon the material. Okay, now let's come to case 1. Case 1 is for metals. Case 1. We just read this in theory. Now we will just draw the diagram. This refers to a situation as shown in figure 14.2a. Okay, so in 14.2a we have two basically. I'll draw both of them in the same one only. I'll explain one after the other. So in the A part, one can have a metal either when the conduction band is partially filled and the valence band is partially empty, or when the conduction band and valence band overlap. So this is the conduction band, this is the valence band. Okay, now let's say this is partially empty. Okay, so the valence band is partially empty and the conduction band is partially filled. Okay, this is filled, these have electrons, and this is partially filled but not completely filled. So if this is the level, let me draw it on a fresh page only. Okay, so we take for case 1, that is metals, we take two cases, A and B. So in the A one, we have this is the highest level of the valence band EV, lowest level of the conduction band EC. This EC, if this is the limit, then the EC is partially filled, you can say. Okay, partially this is filled, and the EV is partially empty. If this is the level, then it is partially empty. Okay, and the distance is less, not too much, it is less. So when this is so when the conduction band is partially filled and the valence band is partially empty, then easily with little amount of electron energy rest, already if they have gone, half have gone, then the rest can also go, right? So this is metal, this is a metal. Now we come to the B part, when they overlap. This I think we just learnt about it. So when the lowest level of the conduction band is lower than the highest level of the valence band, they are just repeating it. Okay, so both are overlapping. The conduction band EC lowest level is below EV, that is the highest level of the valence band. So the electrons which are in the valence band, okay, both are overlapping, they can easily go, there is no space between. Okay, they can easily go to the conduction band. So therefore this is the second case of metals. These are the two cases of metals. When there is an overlap, electrons from valence band can easily move to the conduction band. This situation makes a large number of electrons available for electrical conduction. When the valence band is partially empty, electrons from its lower level can move to the higher level, making conduction possible. Therefore, resistance of such material is low and the conductivity is high. So these are metals we learned before. Their resistivity is going to be low and the conductivity is going to be high. And these are the two cases: partially filled conduction band, partially empty valence band, then it is a metal, and uh, then overlapping valence band and conduction band, then also it is a metal. Now we come to case 2. So what is case 2? In this case, as shown in figure B, large band gap EG exists, okay, which is greater than 3 electron volts. So you need to remember 3 electron volts. If we have case 2 is for insulators. So for insulators, this is EC, lowest level of the conduction band. This is EV, highest level of the valence band. this space, this is greater than 3 electron volt. Okay, this is greater than 3 electron volt. So since this energy gap Eg, okay, Eg energy gap, the gap between the two bands, that is conduction band and valence band, or you can say the lowest level of conduction band, highest level of valence band, when it is greater than 3 electron volt, then all these valence electrons, even if we give them energy, okay, the distance is so high that they cannot possibly go to the conduction band. Okay, so there are no electrons in the conduction band, and therefore no electrical conduction is possible. Note that the energy level is so large that electrons cannot be excited from valence band to the condition band even by thermal excitation. This is the case of insulators. Even if you heat them, still, and if you supply them energy, still they are not able to cross because the energy band gap or the energy gap is very high. So this is insulators. Now we come to the last case, case 3, which is semiconductors. Case 3, semiconductors. So for case 3 semiconductors, this situation in figure 14.2c, you can see here is a finite but small band gap. So here also this is the lowest level of the conduction band EC, highest level of the valence band EV. These are the valence electrons. Okay, now this gap, this is lower than 3 electron volts or lower than that. There is a good amount of gap. Okay, the energy gap is not that less also, but as metals, okay, it is higher, the energy gap here, you can specify it is higher than metals but lower than insulators. So the band gap between so the band gap in semiconductors, it is not as low as metals. It is higher than the band gap in metals, but it is not but it is lower than insulators. Okay, not even that high as insulators. So uh, so because of the small band gap at room temperature, some electrons from valence band energy to cross the energy gap and enter the conduction band. So only some electrons can acquire enough energy to cross this distance and go to the conduction band. These electrons, even though they are small in number, they can move into the conduction band. Hence, the resistance of semiconductors is not as high as that of insulators. Neither is the conduction as high as metals. Okay, it is somewhere in between. That's why we use the word semiconductors. So there are a few electrons in conduction band as well as valence band. It is not completely resisting, it is neither completely conducting. So with that, we finish energy band gaps, and we now can define easily what is a conductor, insulator, and semiconductor. Now we come to only semiconductors. Since the chapter is about only semiconductors, we'll come to only semiconductors. First, we'll see intrinsic semiconductor. Okay, 14.3 intrinsic semiconductor. We shall take the most common case of germanium and silicon, whose lattice structure is shown in figure 14.3. So you can see in figure 14.3, we can see three-dimensional diamond-like structure of carbon, silicon or germanium with a repetitive lattice spacing alpha equal to 3.56, 5.43 and 5.66 Armstrong. So these structures are called diamond-like structures. Okay, and each atom is surrounded by four nearest neighbors. So we know diamond structure, carbon structure, it is uh, four, it is called as diamond like structures because valency 4, so four nearest neighbors, they are connected in the lattice structure, so therefore we call these as diamond like structures. We know silicon and germanium have four valence electrons. Okay, both of them have the valence shell, they have four valence electrons. In its crystalline structure, every silicon or germanium atom tends to share one of its four valence electrons with each of its four nearest neighbor atoms. So in chemistry, we know if eight we need to fulfill. Okay, so when there is a covalent bond, then covalent bond is nothing but sharing of electrons. Covalent bond is nothing but sharing of electrons. So if we need to fulfill all the orbitals, okay, make it completely stable, then each of its four electrons need to be shared with four other electrons of the neighboring cell. You know, no? So like, so this is the case. If this is carbon, 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 then this one is of carbons, but we used to draw like this. Now we take these two, then we take these two, then we take these two, and then we take these two. So one, two, three, four, five, six, seven, 8. So this is now stable. It is fulfilled, or we have fulfilled all the valence. So these shared electron pairs referred to as forming a covalent bond or simply a valence bond. We can say they form covalent bond or valence bond. The two shared electrons can be assumed to shuttle back and forth between the atoms, holding them together strongly. So if this is carbon, it also has a valency of 4. We know, we draw it like this, you know, hydrogen, 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 hydrogen. So for hydrogen, like these two, it is stable. For carbon, this is also stable, this is also stable, this is also stable. All these together makes it stable. So similarly, these two electrons, they can be utilized by silicon also for stability, as well as carbon, because they are sharing here. So therefore here it is written that the two shared electron can be assumed to shuttle back and forth between the associated atom to hold them together, holding them together strongly. Okay, both back and forth. It is to both of their uses. It is being shared. Figure 14.4 schematically shows the two-dimensional representation of silicon or germanium structure shown in figure 14.3, which overemphasizes the covalent bond. It shows an idealized picture in which no bonds are broken, all bonds are intact. Such a situation arises at low temperatures. As the temperature increases, more thermal energy becomes available to these electrons, and some of these electrons may break away, becoming free electrons contributing to conduction. The thermal energy effectively ionizes only a few atoms in the crystalline lattice and creates a vacancy in the bond. The neighborhood from which the free electron with charge minus q has come out leaves a vacancy with an effective charge plus q. This vacancy with the effective positive electronic charge is called a hole. The hole behaves as an apparent free particle with effective positive charge. So, we can see that they have given this schematic two-dimensional structure, okay, wherein all the electrons and how they are bonded, okay, covalent bonds are there between them. It is shown, okay, it is like this. It is shown. So this two, this like that, they have shown nicely. So two electrons. So this and this is here. Then again similarly like this, like this, like this, they have shown, okay. And +4 valency they have put. Now now we can see that it shows idealized picture in which no bonds are broken, all bonds are intact, okay. In the next below in 14.5 you can see the bonds are being broken. So as the temperature increases, okay, so at low temperature no bond is broken, okay. At low temperature all the covalent bonds are intact, okay, with +4 valency and everything is fine. As you go on increasing the temperature, okay, as you increase the temperature, more thermal energy becomes available to these electrons, and some of these electrons may break away. So as you keep increasing the temperature, these electrons, they get more and more thermal energy. As they get thermal energy, they try to break these bonds, okay. They try to break themselves free. As they break themselves free, okay, becoming free electrons, they contribute to conduction, because we know that what is current. It is basically the movement of free electrons, right? So and what are metals? Why metals are conductors? Because they have free electrons. So they break away, they become free electrons which contribute to conduction. The thermal energy effectively ionizes only few atoms in the crystalline lattice and creates a vacancy in the bond. So as they break away, these are electrons, right? So when if we have electrons, okay, and if I say I'm removing one electron, then what will you say? +1 charge. Why would you say +1 charge? Because we know that this one when is anything neutral? When you have one electron and one proton, then it's neutral. If you remove one electron, then it gains plus one charge. If you if protons so cannot be removed. If you add one electron, then it has minus one charge. So extra whatever charge is there, we put that basically. So when you remove one electron, when it breaks free after acquiring or getting thermal energy, then we get a hole. It is nothing but positive charge. Okay, so in that place we get a hole because the electron is gone. So the neighborhood from which the free electron with charge minus q has come out, it leaves a vacancy which has an effective charge plus q. And this vacancy with the effective positive electronic charge is called a hole. The hole behaves as an apparent free particle with effective positive charge. So this hole which has a positive charge, which is formed because the acquired charge minus q has left a vacancy. Okay, neighborhood from which the free electron with charge minus q came out after getting thermal energy leaves a vacancy with an effective charge plus q. This vacancy with effective positive electronic charge is called a hole, that and it behaves as an apparent free particle with effective positive charge. In intrinsic semiconductors, the number of free electrons Ne is equal to the number of holes Nh. Okay, so the number of free electrons, of course, because one electron went, so one hole is created. Another electron went, two holes are created. So the number of the number of free electrons is equal to the number of holes. Okay, and that is equal to Ni. What is Ni? Ni is called intrinsic carrier concentration. Intrinsic carrier concentration. Again, if an electron gets excited, it gets more and more temperature is increased, more and more thermal energy is supplied, then that thermal energy or that heat, it causes the electron to break free from its covalent bonds and become a free electron, contributing to conduction. Okay, and therefore when it this minus q charge, when it breaks free and it moves out, okay, of the crystal lattice, then it leaves a vacancy. This vacancy is basically has an effective positive charge plus q. We call it hole. So the number of free electrons Ne is equal to the number of holes, that is equal to Ni is nothing but intrinsic carrier concentration. Now, semiconductors possess a unique property in which, apart from electrons, the holes also move. How do the holes basically move? It's not like one hole is moving. It's basically, if here is an electron, okay, this moved, then this electron will take its place. So here a hole is created. This electron, because this hole is created, again this is positive, so this will move over here, again here hole is created, again this will move over here, again here hole is created. So now what is happening? Electrons are moving this way. Because electrons are moving this way, holes are moving in the opposite direction. Holes are being formed in the opposite. The hole is going like this because of the movement of electrons. So that's how holes move. So they possess the unique property in which, apart from electrons, the holes also move. Suppose there is hole at site 1 as shown in 14.5a. The movement of holes can be visualized in 14.5b. An electron from covalent bond at site 2 may jump to the vacant site 1 hole. After the jump, the hole is at site 2 and the site 1 has now an electron. Therefore, apparently the hole has moved from site 1 to site 2. So that's what they have said. If site 1 is in vacancy, then the site 2 electron will move over there. So now there's a hole in site 2. So basically the electron has moved, and therefore from the opposite direction the hole has also moved. Note that the electron originally set free is not involved in the process of hole motion. So the electron which has already been freed, which has gone away, it has nothing got to do with the motion of the other electrons moving in and taking its place and the hole moving in the opposite direction. So the free electron moves completely independently as conduction electron, and it gives rise to electron current, i.e. under an applied electric field. So under an applied electric field, the free electron which moved away, okay, which got the energy and left, that free electron when placed under an electric field, it will give us electric current, IE. okay, under an applied electric field. Remember that the motion of the hole is only a convenient way of describing the actual motion of bound electrons. That's what I'm saying, that the motion, the hole doesn't do any kind of motion. The electrons are the ones which do motion, but as they move forward they leave a positive charge or a vacancy, that is called as a hole, and therefore we see that the hole is also moving. It appears whenever there is an empty bond anywhere in the crystal. Okay, so under the action of an electric field, these holes move towards negative potential, giving the hole current IH. So the free electron current is IE, the hole current is IH. The total current I is the sum of the electron current IE as well as the hole current IH. So total current I is the addition of free electron current which is used for conduction IE plus the hole current IH. So now here they are saying that the hole will move towards a negative potential. So what are they basically saying? So if this is the positive potential, this is the negative potential, okay, and positive negative, and here one electron was there, heating, thermal excitation, whatever it is, this electron said that I don't want to be here anymore, I want to go. It went. Now it left a positive space over here, right? And here there were other electrons. Now this electron want to move here, this wanted to move here because here a hole was created. Once it took this place, then here, then here. So finally here a hole was created. So what is happening? The electrons are moving in this direction. The hole is as the electrons are moving, they are leaving holes and that and occupying the other hole. So now the hole which was earlier over here, it has come over here towards the negative potential. Okay, so we will say that the electron is moving towards positive potential, towards positive potential, whereas the hole is moving towards negative potential. Okay, it may be noted that apart from the process of generation of conduction, electrons and holes, a simultaneous process of recombination occurs when the electrons recombine with the holes. At equilibrium, the rate of generation is equal to the rate of recombination of charge carriers. The recombination occurs due to electron colliding with a hole. So we talked about hole coming here, electron going there. How does this happen? This happens because when there is a hole over here, this electron wants to go and take the place of the vacant of the vacancy. Okay, take the fill the vacancy basically. If the electron has gone, okay, so now the vacant which has a positive charge, this negative minus q wants to go and fill that positive electronic charge or the hole, okay, which is vacant. Okay, so it goes and it recombines. This is the recombination process. As it recombines, it forms another carrier charge that is positive over here. Then this electron goes and recombines with this positive charge or hole which is vacancy, and here another hole is formed. Similarly, this keeps happening. So this combination that is taking place of are taking the place of the vacant electron or vacant charge, combining with a hole, electron combines with the hole, this is called as recombination. And when another hole is formed, it is known as the generation. Okay, generation of electrons. Okay, so at equilibrium, the rate of generation is equal to the rate of recombination of charge carriers. So when we are at equilibrium, then the number of holes which are created is equal to the number of holes which are being recombined. So the combination occurs due to electron colliding with a hole. Okay, these two figure 14.5 A and B, these two are really important. Now, an intrinsic semiconductor will behave like an insulator when T is equal to 0 Kelvin. It is the thermal energy at higher temperature, that is T is greater than 0 Kelvin, which excites some electrons from the valence band to the conduction band. So, intrinsic semiconductors, we need to remember 2-3 things about it. First is that for intrinsic semiconductors, they are pure semiconductors. Intrinsic semiconductors are pure semiconductors. If I said silicon, germanium, then germanium. There is no other element is being involved. Then another second point is that they need external heating to for otherwise they will behave like to work, otherwise they will behave like insulators, else they will behave like insulators. Okay. So an intrinsic semiconductor will behave like an insulator when at T is equal to 0 Kelvin. So if this is the conduction band, this is the valence band. Okay, so when T is equal to 0 Kelvin, in the valence band, the electrons are still there, nothing is going up. Okay, the but the moment the thermal energy is T is greater than 0 Kelvin, okay, then it excites some electrons from valence band to the conduction band. So some electrons will go to the conduction band. These thermally excited electrons at temperature greater than 0 Kelvin, they partially occupy the conduction band. Therefore, energy band diagram of an intrinsic semiconductor will be shown in 14.6b, wherein there are electrons in valence band 2, there are electrons in conduction band 2, and the conduction band has been partially occupied by electrons. This is how we represent an intrinsic semiconductor. Here some electrons are shown in the conduction band. These have come from the valence band, leaving equal number of holes over there. So what we have to do is, when we show this diagram and when we show that the conduction band is partially filled, okay, and then we need to show the electrons which have moved. Okay, uh, so there we need to either darken the other circles and leave these empty and label them as vacancy, energy vacancy, or we can put positive sign also. Okay, so equal number of holes, if 4 are there, then here also 4 holes should be there. We need to show that. Example 14.1, carbon, silicon and germanium have same lattice structure. Why is carbon an insulator, why silicon and germanium are intrinsic semiconductors? This is because energy required to take out an electron, that is the energy gap ionization energy, is most less for germanium than silicon and highest for carbon. So even though now we here took silicon and germanium, right? We did not take carbon, even though, and we are saying silicon and germanium have diamond like structure, like carbon also has carbon like structure, and everything we are saying allotrope of carbon like structure. So but then we are not taking carbon. Why? Because carbon is an insulator, it cannot be a semiconductor, because its energy gap is higher, and no matter how much ionization energy we give, still the electron cannot be excited and go to the conduction band. Therefore it is not a semiconductor, it is an insulator. Okay, and we also know through periodic table that silicon, germanium, so this the metallic, it increases, so therefore it is easiest for germanium to for electron to get excited and go, then silicon, and finally carbon. Now extrinsic semiconductor. So we did intrinsic semiconductor, now we come to extrinsic semiconductor. The conductivity of an intrinsic semiconductor depends on its temperature, but at room temperature its conductivity is very low. Right, so we need external heating in intrinsic semiconductor. No important electronic devices can be developed using these semiconductors. So since at room temperature the conductivity of intrinsic semiconductors is very low, we cannot as such make any important electronic devices with those semiconductors. Hence there is a necessity of improving their conductivity, and this can be done by using impurities. What is impurity? Impurity is basically when you add another element. Okay, when you add another substance, any something else also along with the main what you have taken, silicon and germanium, along with that I'll add some other element also, then those are known as impurities. When a small amount, say a few parts per million of a suitable impurity is added to a pure semiconductor, the conductivity of the semiconductor is increased manifold. Whenever you add to a pure semiconductor, silicon or germanium, let's say we add another few small amount parts per million of another substance, then the semiconductor's conductivity increases. Such materials are known as extrinsic semiconductors, or you can also say impurity semiconductors. The deliberate addition of a desirable impurity is called as doping. So what is doping? Doping is a deliberate addition of a desirable impurity in order to increase the efficiency of a semiconductor or increase the conductivity of a semiconductor. The impurity atoms are called as dopants. So the material, the impurity or the materials which we add, they are called as dopants. Such a material is therefore called as the doped semiconductor. So we call extrinsic semiconductors are called as extrinsic semiconductor, as well as impurity semiconductor, as well as doped semiconductor. The process of deliberately adding an impurity in order to increase the efficiency of and conductivity of a semiconductor is called as doping, and the materials or the substances added are called impurities added are called as dopants. The dopant has to be such that it does not distort the original pure semiconductor lattice. So we need to add a dopant which does not distort the original pure semiconductor lattice. It should not react or chemically disturb the entire lattice structure only. No. Unnecessary condition to attain it occupies only very few of the original semiconductor atom sites in the crystal. It should only occupy some of the original semiconductor atom sites, okay, and therefore increase the overall conductivity. A necessary condition to attain this, that the size of dopant and semiconductor atoms should be nearly the same. A good way to not disrupt the lattice structure of the original semiconductor but only few atom sites is to choose a dopant whose atom size is nearly same as that of the semiconductor. So there are two types of dopants used in doping the tetravalent silicon or germanium. So to dope the tetravalent silicon or germanium, we have two types of dopant. One is pentavalent, which has valency of 5, that is arsenic, antimony, phosphorus, etc. Okay, the other one is trivalent, which have valency 3, that is indium, boron, and aluminium, etc. We shall now discuss how the doping changes the number of charge carriers and hence the conductivity of semiconductors. Silicon or germanium belongs to the fourth group of the periodic table, and therefore we choose dopant elements which are nearby, that is fifth or third, expecting and taking care of the that the size of dopant atom is nearly same as that of silicon or germanium. Interestingly, the pentavalent and trivalent atoms in silicon or germanium give two types of entirely different semiconductors. Okay, so what is the difference between extrinsic and intrinsic semiconductors? Intrinsic semiconductors are pure semiconductors, whereas extrinsic semiconductors are not pure semiconductors. They contain impurities within them. Okay, and external heating is required in intrinsic semiconductors, whereas otherwise they behave as insulators at room temperature, whereas this is not required in extrinsic semiconductors. Now extrinsic semiconductors can be of in extrinsic semiconductors for silicon and germanium, that is both are which tetravalent, to increase their conductivity and efficiency of the semiconductor, we can use the for doping we can use dopants which are of two types. One can be the dopants which are pentavalent, that is have the valency of 5. The other can be the dopants which are trivalent, which have the valency of 3. So pentavalent, the elements are pentavalent, the elements would be arsenic, antimony, and phosphorus, whereas trivalent, they would be indium, boron, and aluminium. Okay, why do we choose valency either 3 or 5? This is because we saw that in order to not distort the entire lattice structure, we need to choose dopant atoms which have the same atomic size as that of the atom of um, uh, the we are taking the initial silicon or germanium. Okay, so the silicon or germanium atom size and as well as the dopant atom size should be nearly the same. Therefore we since both silicon and germanium are tetravalent, we are taking pentavalent and trivalent elements so as to not change anything. Now the main differences between intrinsic semiconductors and extrinsic semiconductors, let me write them down. So intrinsic, extrinsic, they are pure, as I said. Okay, they have impurities. I'm just writing in short, you can elaborate later. So they are pure semiconductors, whereas extrinsic, they have impurities. They the majority charge here, majority charge conductors. Okay, what are majority charge conductors? As you can say, majority charge who can conduct. Okay, majority charge conductors in intrinsic would be both electrons as well as holes, because we said now that the number of free electrons is equal to the number of holes, and then we saw that the electric current that is from hole by holes as well as this gives us the total current, and IE is equal to IH is equal to IN, that is the intrinsic that is the intrinsic carrier concentration. Yeah, whereas over here majority that we will read ahead, majority is different. Okay, it can either be electrons or holes, not both of them. Okay, now p type it's hole, for n type it's electron. Now the conductivity over here is less and it depends on external temperature. As I said, you need external heating, and the conductivity is also less because at zero at zero temperature nothing we don't get semiconductor, no electrons are excited. Okay, there's nothing, the conduction band is empty at 0 Kelvin. We need uh, more than 0 Kelvin temperature, good amount of to in order for the excitation to occur, so conductivity is also less. Whereas and the example are germanium and silicon. Okay, so these are elemental semiconductors, right? Nothing else is there, only this is there. Whereas for extrinsic, conductivity is high, and conductivity of course over here is high, and it does not only depend on temperature, it depends on temperature as well as the quantity of impurity, the quantity and quality of impurity, actually quantity of impurity, because we are going to use trivalent pentavalent only. Quantity of impurity, that is atoms added. Now this examples would be phosphorus doped with silicon, or anything else also. One phosphorus we took for pentavalent, we can take aluminium doped with germanium. Okay, now let's come to p type and n type. Okay, so first we'll see n type semiconductor. N type semiconductor. Okay, just a second. Okay, so first is n type semiconductor. Okay, so suppose we dope silicon or germanium with pentavalent element as shown in figure 14.7. Okay, so n-type semiconductor, when we dope silicon or germanium with a pentavalent impurity or dopant, then we call them as n-type semiconductor. Okay, when an atom of plus 5 valency element occupies the position of an atom in the crystal lattice of silicon, 4 of its electron bond with 4 of silicon neighbors, while the fifth remains weakly bound to its parent atom. This is because the four electrons participating in bonding are seen as part of. Okay, so when I say p type and n type, it's very self-explanatory that you know which one has more electrons and which one has more holes. Okay, when I say p type and when I say n type, okay, we know n type is pentavalent, has pentavalent dopant, okay, and p type has trivalent dopant. And we know that these dopant are we are combining them with either silicon or germanium, right? So we know that silicon germanium both have valency 4, right? So if this is 4, okay, here also 4. So for p type trivalent we only have 3, right? So here one is going to remain, this is going to be a hole, right? So there are going to be more number of holes because there are 4. We need to we need for to fulfill all, okay, um, to fulfill all, to make it stable we need 4 more electrons of the dopant in order to satisfy, whereas we only have 3, right? So one will be whole, whereas over here we have 5, whereas we only need 4. So this, it's already fulfilled, so this one electron is leaving out every time. So here electron is going to be more, here holes are going to be more. This is, I think, very self-explanatory. So now we are just going to elaborate these 2 points only ahead more and more and more. Okay, so suppose we dope silicon or germanium with pentavalent element. When an atom of plus 5 element occupies the position of an atom in the crystal lattice of silicon, 4 of its elements bond with 4 of silicon neighbors, while the fifth remains weakly bound to its parent atom. Okay, fifth one is weakly bound to its parent atom. This is because 4 electrons start participating in bonding and they are seen as part of the effective core, okay, by the fifth electron. So when all 4 of these electrons they start all 4 of these electrons start participating and they completely nicely bond, okay, then this fifth electron, from its perspective if we see, then these are all part of core. Okay, now it is completely stable. Now silicon atom has got 4 more electrons and it is completely stable now. As a result, the ionization energy required to set this electron free is very small. Even at room temperature, it will be free to move into the lattice of semiconductor, right? Because this is not bonded very strongly. This is just weakly bound to the parent atom. Nothing like that. Even if with little energy, this at room temperature also this electron will cross the band gap. Okay, will cross the Eg and it will go to the conduction band from the valence band. Okay, so um yeah, so for example the required energy 0.01 electron volt. Okay, so for germanium and 0.05 electron volt for silicon, right? So um to separate this electron from its atom. This is in contrast to the energy required to jump the forbidden band, about 0.72 electron volt for germanium and about 1.1 electron volt for silicon at room temperature with intrinsic semiconductor. Please underline this. This is really important. Even I was remembering. I don't remember these values very well. Okay. So for this electron, okay, the energy required for in germanium as well as silicon crystal. 0.01 electron volt is the it needs to jump or cross, and 0.05 electron volt in silicon, okay, to separate this electron from its atom. Only that much. This is in contrast to the energy required to jump the forbidden band, okay, which is 0.72 electron volt and 1.1 electron volt at room temperature in an intrinsic semiconductor. When we take an intrinsic semiconductor, 0.72 and 1.1 electron volt distance is there. Whereas for extrinsic, for this particular fifth pentavalent atom, it is pentavalent electron, it is only 0.01 electron for germanium, 0.05 electron volt for silicon. Now thus the pentavalent dopant is donating one extra electron for conduction, and hence it is called as a donor impurity. Why is it called as a donor impurity? Because uh, every time the dopant is being used, okay, one electron is being left out every time. So therefore it is a donor impurity. The number of electrons made available for conduction by dopant atom depends strongly upon the doping level and is independent of any increase in ambient temperature, okay. Number of electrons which are available for conduction by the dopant atoms, it depends strongly upon the doping level. How much are we doping, how are we doping, okay. And uh, and it is independent of any increase in ambient temperature. In room temperature only, if it can easily cross 0.01, 0.05 electron volt, then it doesn't matter how much we increase, because at the end of the day, no matter how much we increase for pentavalent, the other four electrons are going to be strongly bonded, and they are going to stabilize, and they are going to become core, okay. They are going to completely fulfill the orbitals of silicon atoms. So no matter how much ambient temperature we increase, at the end of the day it depends on how much we dope. So how, as higher as we dope, that many free electrons we get, because every time we dope, one free electron is going to be available for us for conduction. So on the other hand, the number of free electrons with an equal number of holes generated by silicon atom increase weakly with temperature. Okay, so the number of free electrons, okay, with an equal number of holes. So these free electrons, of course, valence band, they have equal number of holes which are generated by the silicon atom. They increase weakly with temperature. Okay. So, in a doped semiconductor, the total number of conduction electron Ne is due to the electrons contributed by donors and those generated intrinsically, while the total number of NH is only due to holes from the intrinsic source. So that's what I just said. That this is the core. Okay, this is the core, and no matter how much we increase the temperature, ambient temperature, it's not going to affect it that much, because it is completely stabilizing the silicon atom, okay. So when I say Ne, then Ne is due to the Ne is the number of free electrons. The number of free electrons every time we do doping, that is due to this free fifth electron, as well as intrinsically, if we break the covalent bond and one electron is there. But when I say NH, that's why in between I stopped, the next line when it said it increases weakly with temperature, I stopped there, because the holes are not being generated at all by. Then next line I found out that they are actually talking about what is happening intrinsically, as well as what is happening for the fifth pentavalent electron. So the holes are not being generated by the pentavalent electron, because the pentavalent electron is not taking as such a place at all, okay. So the NH, the number of holes, is only due to intrinsically the electrons which have been freed, okay. Only those holes. When we say we are counting the holes, we are not counting holes every time fifth electron, because the fifth electron is already free. It is not strongly bonded with the silicon atom. It does not have such a place. Okay, in a doped semiconductor, the total number of conduction electrons Ne is due to the electrons contributed by donors and those generated intrinsically, while the number of holes is only due to the holes from the intrinsic source. But the rate of recombination of holes would increase due to increase in the number of electrons, right? So when I say that the number of electrons is due to the donors, as well as that generated, as well as those electrons from intrinsically, but the holes are only for intrinsic, then Ne over here is much higher than Nh. So when I say recombination is occurring, then all these electrons will try to recombine with the number of holes, but the number of holes are lesser, so the holes will get fulfilled, but still electrons will be remaining. Okay, so now the rate of recombination is also higher. So as a result, the number of holes would get reduced further because the number of electrons are higher than the number of holes and recombination is occurring. Okay, so now the holes will even reduce further. Okay, thus with proper level of doping, the number of conduction electron can be made much larger than the number of holes. If we properly dope it, then Ne will be much higher. Okay, if we properly dope it, because every time we are getting 1/5 electron which is already free, as well as through increase in temperature and proper doping level, we are also getting an intrinsically free electron. Okay, and this is what Ne. Hence, in an extrinsic semiconductor doped with pentavalent impurity, that is N type, the electrons become majority carriers and holes are the minority carriers. So over here, for N type, electrons are the majority carriers, whereas the holes are the minority carriers. Okay, so Ne is greater than Nh. And this is really important. These semiconductors are therefore known as N-type semiconductors. Now we come to P-type semiconductors. How much? It's already 1 hour 26 minutes. Alright, now we come to P-type. We'll finish P-type, then for part 2 we will do PN junction diode, semiconductor forward bias, reverse bias, rectifier, and then again rectifier. Till that only it will take a lot of time, because like it needs to be explained very nicely. After that, if still it gets over in less than an hour, then we will go for Zener diode, photodiode, light emitting, solar cell, and not or nor and all those things. Okay, now, P-type semiconductor. P-type semiconductor, this is obtained when silicon or germanium is doped with trivalent impurity like aluminium, boron, indium, etc. The dopant has one valence electron less than silicon or germanium, and therefore this atom can form covalent bonds with neighboring three silicon atom, but does not have any electron to offer the fourth silicon atom. So we already discussed this. Here we take trivalent dopant, okay, trivalent impurity. So trivalent, we know silicon has 4 valency. It is going to need 4, and we are only providing it 3. So what about the one valence electron which is left? Okay. So therefore, this atom can form covalent bonds with neighboring 3, but it does not have any electron for the fourth atom at all. This is empty. Okay, so the bond between the fourth neighbor and the trivalent atom has a vacancy or a hole. Okay, so this is a hole. Okay, so because of this hole, uh, since the neighboring silicon atom in the lattice wants an electron in place of a hole, an electron in the outer orbit of an atom in the neighborhood may jump to fill this vacancy, leaving a vacancy or hole at its own site. Okay, so thus the hole is available for conduction. Note that the trivalent foreign atom becomes effectively negatively charged when it shares fourth electron with neighboring silicon atom. Again, let's read this. Since the neighboring silicon atom in the lattice wants an electron in place of a hole, an electron in the outer orbit of an atom in the neighborhood may jump to fill the vacancy, leaving a vacancy or hole at its own side. Okay, so the silicon atom now, it's really sad. Okay, it needs to be bonded. It needs to be fulfilled. So basically, in the orbit, okay, any other atom will be there. He'll be like, hey, give me one, share with me, okay, I need to fulfill. So one electron will come and it needs to fulfill basically, okay, jump to fill its vacancy, leaving a vacancy or hole at its own side. खुद के साइड पे उसको बेचारे का होल हो जाएगा, बट स्टिल उसको आके इसको फुलफिल करके जाना है, खुश करके ही जाना है. ओके, सो so thus the hole is available for conduction. Okay, the hole now is available for conduction because again it's traveling, right? So another electron will come take its place, another electron will come take its place, so it is basically it is available for conduction. Therefore, no, note that the trivalent for an atom becomes effectively negatively charged when it shares fourth electron with neighboring silicon atom. Okay, when it shares its fourth electron, okay, with neighboring silicon atom, then it becomes negatively charged, effectively negatively charged. Okay, therefore the dopant atom of p-type material can be treated as core of one negative charge along with its associated hole, because now it took one, right? So it has become negatively charged, this has become negatively charged. So this p-type material or this dopant, okay, it can be called as, can be treated as core of one negative charge along with hole, along with hole. Okay, it is obvious that one acceptor atom gives one hole. These holes are in addition to the intrinsically generated holes, while the source of conduction electron is only intrinsic generation. Again the opposite happens. Over there what happened, we had extra electrons, okay, but the holes were only due to intrinsic. Over here we have holes due to this trivalent dopant, as well as intrinsically we electrons were freed and holes were formed, okay, because of both of these, whereas electrons are only because intrinsically the electrons were freed. Okay, so then over here again the holes are greater than the number of electrons again. So thus for such a material the holes are the majority carriers and the electrons are the minority carriers. So over here the holes became the majority carriers, whereas the electrons became the minority carriers. Okay, p type is exact opposite of n type. So n-type you need to remember more electrons, p-type you need to remember more holes. Therefore, extrinsic semiconductors doped with trivalent impurity are called p-type semiconductors. For p-type semiconductor, recombination process will reduce the number of intrinsically generated electrons to any. We have for p-type, okay, so when recombination will occur, okay, when recombination will occur, then these electrons will go and recombine with the holes, but the holes are so much that these electrons, they, even though they will reduce significantly, the number of holes will not end. Okay, the still number of holes will be remaining. Now note that the crystal maintains an overall charge neutrality, as the charge of additional charge carrier is just equal and opposite to that of the ionized core in the lattice. So the crystal, it has been maintaining an overall charge neutrality, okay, as the charge of additional charge carriers is just equal and opposite to that of the ionized core in the lattice. In extrinsic semiconductors, because of the abundance of majority current carriers, the minority carriers produced thermally have more chance of meeting majority carrier and thus getting destroyed. Okay, so the crystal at the end, it maintains an overall neutral charge only, because the charge of additional charge carrier is just equal and opposite to that of the ionized core. Okay, because in this you saw that together it becomes negative, right? Negative charge core, the core becomes negative because another electron is coming, okay, but then the holes are more, so that is positive. Hole is nothing but positive charge carrier, right? Like positive, it has positive electronic charge, so basically it is becoming neutral at the end of the day. Similarly over there also, number of free electrons were more, Okay, so since number of free electrons are more, so automatically the core becomes positive. But then the free electrons, since electrons are more, therefore at the end of the day, through recombination and all, again the overall crystal becomes electrically neutral. So, in extrinsic semiconductors, because of the abundance of majority current carriers, the minority carriers produced thermally have more chance of meeting majority carriers and thus getting destroyed. Therefore, abundance of since there is abundance of majority current carrier, minority carriers which are produced thermally. Okay, you we saw that both in p-type as well as n-type, the minority current carriers, they were only dependent intrinsically, right? Because of the dopant, both the times in n-type also electrons were higher because dopant plus intrinsically produced electrons, whereas in p-type intrinsically produced holes as well as the dopant holes by the dopant, both were there. So both of them minority charge carriers are the ones, or current carriers are the ones which have been produced thermally. They have more chance of meeting majority carriers and getting destroyed. That's what in those, I said now that electrons are so much and holes are so less in n type, that all of these will combine and these will get destroyed, these will recombine and these will end, and still electrons will be remaining. Similarly over here also, the electrons, they will go and go and go and these will get reduced and destroyed, but still holes will be remaining. So hence the dopant, by adding a large number of current carriers of one type which become the majority carrier, indirectly helps to reduce the intrinsic concentration of minority carriers. So by adding large number of current carriers of one type which become the majority carriers, indirectly it reduces the intrinsic concentration of minority carrier. The semiconductor's energy band structure is affected by doping. In case of extrinsic semiconductors, additional energy states due to donor impurities ED, okay, and acceptor impurities EA also exist. Because in semiconductor, so in case of extrinsic semiconductors, additional energy states are there due to donor impurity and acceptor impurity. So in pentavalent, we saw one free electron was there. Then trivalent, now for p type we are seeing that one extra hole is there. So different energy states are also there in the energy band diagram of n type semiconductor. And silicon semiconductor, the donor energy level is slightly below the bottom conduction EC of the conduction band, and electrons from this level move into conduction band with very small supply of energy. At room temperature, most of the donor atoms get ionized, but very few atoms of silicon get ionized. So the conduction band will have most electrons coming from donor impurities. Similarly, for p-type semiconductor, acceptor energy level EA is slightly above the top of valence band. With very small supply of energy, electron can jump to the level of EA and ionize the acceptor negatively. Okay, so over here in the diagram, for n-type semiconductor, we have the donor impurity ED, okay, and for p-type semiconductor we have the acceptor impurity energy level EA. These both are created, right? So the so I'll tell you what they are exactly trying to say over here. Okay, so for extrinsic semiconductors in n type and p type, along with intrinsically, excited electron and hole, we also have over here free electron, one extra free electron, and over here one extra hole, right? So what they are saying is that this for this free electron, there is one energy level, extra energy levels are created for these two, and so they are saying that the dopant, uh, okay, in case of extrinsic semiconductor, additional energy states are there due to donor impurity and acceptor impurity. So one extra ED is there. We saw na 0.01 electron volt for this free electron in germanium and 0.05 electron volt in silicon for this free electron. Whereas if it would have been intrinsic semiconductor, for intrinsic semiconductor it is 1.1 and something else, right? So it is very high, but for this free electron it is not. What was the exact 0.72 for germanium and 1.1 for silicon, it was there. Okay, and at 0 Kelvin it was not conducting. But for this free electron, the donor impurity level, and for this hole, the acceptor impurity level, they are lower. So when we draw, okay, for n type, since this is EC and this is EV, okay, valence band, conduction band. So for n type, okay, when T is greater than 0 Kelvin, of course, because the intrinsic are also going up, okay, crossing and going up. The free electrons over here, the energy band of n-type semiconductor, the donor energy level ED is below the bottom or the lowest level of the conduction band, and electrons from this level move into the conduction band with very small supply of energy. Okay, so the free electrons ED, donor impurity level, the electrons over here, they are just below the lowest level of conduction band and they easily move. Okay, and temperature is greater than 0 Kelvin, so from valence band also they are moving. Okay, intrinsically also they are moving, free electrons are also moving. This is for n type semiconductor. Now for p type semiconductor, again we have EC, again we have EV, sorry, again we have EV, and then we have conduction band EC, I'm so sorry. Now here we have again valence electrons, right? So over here we see that for p type, okay, get ionized, but few atoms of Si get ionized. So conduction band will have most electrons coming from donor impurities, because free electrons over here are more, right? Here free electrons are more because pentavalent, four get attached, one is remaining. Free electrons are more, so most of them they will come from here only, donor impurity only. Now for p-type semiconductor, acceptor energy level, that is EA, it is right above EA, acceptor energy level EA, is slightly above the highest level of the valence band. Okay. So with very small supply of energy, an electron from valence band can jump to this level and can ionize the acceptor negatively. Okay, so with very small energy, the electrons can go to the acceptor band and they can ionize this negatively. Okay, alternately, we can also say that with very small of energy, the hole from level A sinks down to the valence band. So basically, we can either say that this electron, so what we learned in p-type was that if this is silicon and there are electron, this is done, this is also fulfilled, this is also fulfilled, this is not fulfilled, then we saw now that another atom from another electron from another atom will come and do this, fulfill this. So either we can say that electrons on the valence band go to the acceptor energy level, and over there they fulfill, either we can say they fulfill the dopant, which is trivalent, they make it tetravalent, they fulfill the electron, they go over here. Or we can say that the hole which is created, the moment they fulfill this, the whole this a hole will be created over here, right? If an electron goes and fulfills this, gets recombined, then in its place one hole will be created. So either we can say that the hole is moving, or we can say that the electron from valence band with little energy goes to the acceptor impurity and creates a negative charge over there. We also saw now that the core becomes negatively charged because an electron from another atom comes and forms a covalent bond and takes the place in order to satisfy the silicon atom or make it fully stable. So we can say this. Okay, so these are the two ways that we can say what happens for acceptor energy level. Now electrons rise up and holes fall down when they gain external energy. At room temperature, most of the acceptor atoms get ionized, leaving holes in the valence band. Okay, at room temperature, most of them they will get ionized, and there will be more number of holes in the valence band. Thus, at room temperature, density of holes in the valence band is predominantly due to impurity. So over here, most of the electrons which were there in the conduction band, okay, these were due to the impurity, okay, at room temperature, because at room temperature you know that intrinsically cannot we cannot go, okay, whereas intrinsically no conduction occurs, whereas over here we can say that the maximum number of holes in the valence band is due to yeah, is due to again the acceptor impurity, because at room temperature so many holes cannot be there in the valence band, because that many electrons at when T is equal to 0 Kelvin do not excite to the conduction band. So the electron and hole concentration in semiconductor in thermal equilibrium is given by Ne into Nh is equal to Ni square. Electron and hole concentration in a semiconductor in thermal equilibrium is given by Ne, that is number of holes into Nh, sorry, number of electrons into Nh, number of holes, that is equal to Ni square. That is the current square. So the though the above description is grossly approximate and hypothetical, it helps us in understanding the difference between metals, insulators and semiconductors, intrinsic as well as extrinsic, in a simple manner. Difference in the resistivity of carbon, silicon, germanium depends upon the energy gap between their conduction and valence bands. For carbon, that is diamond, silicon, germanium, energy gaps are 5.4 electron volt, 1.1 and 0.7 electron volt. So for it is highest more than 3 electron volt for carbon. That's why it is an insulator, that's why it is not a semiconductor. Whereas 1.1 electron volt and 0.7 for silicon as well as germanium, therefore both of them are less than 3 electron volt, and therefore they are semiconductors. Sn is a group 4 element, but it is a metal because the energy gap is 0 electron volt. Okay, Sn is also group 4 element. Okay, but the energy gap, okay, so Sn is 10, I guess. Yeah, so Sn is 10. So because of which the energy gap is 0 electron volt, so therefore it is a metal. Suppose a pure silicon crystal has 5 into 10 raised to power 8 atoms meter cube. It is doped by 1 ppm concentration of pentavalent arsenic. Calculate number of electrons and holes given that Ni is equal to 1.5. So we know that Ne is equal to Nh is equal to Ni square. So we know what is Nh, we know what is Ni. So we need to find out Ne. So we will do Ne into 5 into 10 raised to power 28 is equal to 1.5 to 10 raised to power 16 whole square. So we get the answer. Okay, so this was part 1, semiconductors. We completed p-type as well as n-type, p-type, n-type in extrinsic semiconductor. We did intrinsic semiconductors. We studied about the energy bands as well as uh, the introduction of semiconductors. So this is part 1, and part 2 of semiconductors I'll I'll upload. Okay, semiconductors part 1. Okay, NCRT. Part 2 we will start from PN junction diode. Okay, again thank you so much and have a good day.